Okay, in this section, we're going to be looking at some more properties of functions and graphs that we kind of need to look at. First, we're going to look at boundedness. We look at whether graphs are bounded below, bounded above, or both. And if they're bounded both above and below, we just say they're bounded. Bounded below means it has basically an absolute minimum point. You look at bounded below means you're going to look at what's happening on the floor of the function. Bounded above means you're going to be looking at what happens at the ceiling of the function, and that means it tops out somewhere at a high point on the graph, okay? And then bounded means it does both, okay? So here's some examples. If I look in this case at what's happening at the ceiling of the function, and by the way, you can assume that these have arrows and do go on to infinity. Unfortunately, the book doesn't draw them in. But because they don't reach an absolute height at the ceiling, they go to infinity, it is not bounded above. Same thing happens down here at the floor of the function. Down here at the floor, they'll never reach a bottom point down there. And so it is not bounded either above or below. So we say it's unbounded. Okay. This one, if we look at the ceiling, it goes to positive infinity up here, right? I will never reach a maximum point. And so it is not bounded above, but it does reach a minimum point down here at the ceiling, or at the floor, I mean. Okay, so it is bounded below. This function, I would say, is bounded below. This function is unbounded. This function is bounded below. Okay, we're going to look at a couple more. This one, if I look at the floor of it, it doesn't reach a minimum point, so it is not bounded below, but it does reach a maximum point up here, so it is bounded above. And then this one reaches both a high point and a low point. So at the floor it reaches a high, or I'm sorry, at the ceiling it reaches a high point, at the floor it reaches a low point. So it's bounded both above and below. And then instead of saying bounded above and below, we just say it's bounded. Okay. So here's some examples. Again, the arrows are not drawn in, but you can assume that this goes to infinity up here. This reaches the at the floor. It does have an absolute minimum. So I can say that this right here, I'm trying to do this with my pen. Sorry, I need to, or my mouse, I need to pick this up. I can say that this down here is bounded below. Okay, not above, but only below. This one reaches a low point here and it reaches a high point here. So it's bounded both above and below. So instead of saying that, I just say it's bounded, which covers both of them. Okay. All right, then we're going to look at local maxes and local mins. And it's easiest to see this in a graph so that you can kind of do this, okay? This is asking us to look at functions that have local maxes and local mins and then define them, okay? You can assume that this goes to infinity up here, okay? This down here, and you can kind of tell that the coordinate is about, we're going to say -2, -23. We're estimating a little bit, but it asks us to estimate, okay? And we can do that. So that right there, actually, I would say this about that point. It is the lowest point on the graph. By the way, this graph would be bounded below, not above, but it is the lowest point on the graph, which means I would say this. This has an absolute min of -23. Notice that's your y value when x is about -2. Okay, and I maybe should say that this is about -23 because I'm estimating this from my graph, but that's what I would say about that point. Okay, then the absolute highest point this graph reaches is infinity because it does at the ceiling go all the way to infinity. However, you've got some highs and low points within the graph, which one of them would be right here. So this is the highest point of anywhere around it. So this point right here would be a local max. It's not the highest point on the entire graph, but it's the highest point of everywhere around it. So you would call it a local max. And I would say that that y value is about 1 when x is about 0.5. Okay, that's what I would say about that point. And then this point right here is a local min because it's the lowest point of anywhere around it. It is not the lowest point forever on the graph, but it is the lowest point of everywhere around it. So I would say this is a local min of about, I don't know, -2 when x is about 1.5, let's say. Okay, we're estimating a little bit, but that's what you do. Okay, and we'll do this on our calculators too, and actually maybe I should do it on your calculators, okay? Let's just do this on your calculators so that you can kind of picture how this goes. We're going to change our windows so that we can see everything. So x to the fourth minus 7x squared plus 6x. I have to see if I can remember that number or that equation. X to the fourth minus 7x plus 6, is that what it was? I have to look again, see? X to the fourth minus 7x squared plus 6x. I was close. Minus 7x squared. Oh, God, I've really messed this up. Minus 7x squared. There we go, plus 6x. Okay, we're going to change our window so that it's closer to what this one looks like. Notice my x values are going from -5 to +5. My y values are going from -35 to +15, and they are going up by 5s. Okay, so I will change my window so that we can see this. My x values went from -5 to 5, and it went up by 1. My y values went from -35 to 15. And they went up by 5s. So if I graph this now, it should look somewhat similar to how our graph looks. It takes a little bit. And what did I do? Maybe this wasn't the graph that I graphed. Oops, that's because I have a times in here and not a plus. All right, let's try that again. There we go. I don't think it's quite right. But anyways, I'm going to just teach you how to find local maxes and local mins. So here's what you do. You go second trace, okay? And we are going to find a max or the min. So let's find a maximum point, okay? I know that I have a maximum point right here. So notice your calculator is asking you to do left bound. You want to put your cursor just a little bit left of that high point and hit enter. And then a little bit right of that high point and hit enter. And then right on that high point and hit enter. And I would say that my local max is 1.32 when my x value is about 4.55. Okay, that's what I would say. And then of course I could do local mins too by doing second trace. Number 3, let's look at this point right here. Okay, I'll put my cursor a little bit left of that point, hit enter, a little bit right of that point, hit enter, right on that point, hit enter, and you can get it pretty exactly on your calculator. Okay, so my local min would be -1.77 when my x value is about 1.6. Okay, so that's how you do those on your calculators if you need to. All right, then we're going to be looking at some horizontal and vertical asymptotes. Okay, again, horizontal or vertical asymptotes are basically places where your function is undefined. So I can see graphically that I have vertical asymptotes here and here. It looks like it's at -1 and 2. If we think about factoring this, it does factor as -2 and +1, which means x equals -1 here and x equals 2. If x is -1 or x is 2, either one of those would result in having a 0 in the denominator, and I can't have a 0 in the denominator. So I do have vertical asymptotes at x equals -1 and x equals 2. Okay. And then this one is a little bit tricky, but I would say that I have a horizontal asymptote here. And here's how you can kind of tell. put in really big numbers and look at what's happening as you move off the right edge of your graph. As you move off the right edge of your graph or the left edge of your graph, either one, both of those lines are approaching the y-axis, which is where, or sorry, the x-axis, which is where y is 0. Okay, so in this case, I have a horizontal asymptote at y equals 0. Okay. All right, we're going to do another couple of these. Maybe not. End behavior tells you what's happening on either the left side or the right side of a graph, or as it approaches a certain number. You'll look at. I'll show you some of these in a minute here. Okay. So we are going to analyze the end behavior of these functions. We're going to graph these on our calculator, and we're going to kind of see what happens. So first of all, we will put in 3x squared over x squared plus 1. 3x squared over x squared plus 1. All right, let's hit enter. And actually, I'm going to hit zoom 6 because my window is all off. Okay, so when we look at end behavior, we look at what's happening on either end of the graph. Okay, so in this case, if I look at this side over here, I'm asking you to figure out, as my x values approach infinity, positive infinity, my x values are getting bigger and bigger and bigger and bigger. All of this is telling me is that I'm moving off the right side of the graph. My x values are moving to the right. They're getting closer to infinity. I want to know, and by the way, I should put this function in here. Let me erase this circle. I want to know what your y values are as your x values go to infinity. And my function was, I don't remember what it was again, 3x squared over x squared plus 1. Whoops. Okay, what gets filled in right here is what your y value should be. Okay, what are your y values getting really, 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 really close to? And hopefully you can see from the graph that they are getting really, really close to 3. If you can't see that from the graph, you should be able to look at your table and continue to scroll down, and you can get bigger and bigger and bigger and bigger and bigger numbers, and you can see that they're getting really, really close to 3. They're never touching 3, but they're getting really, really close to 3 as you scroll. Okay, and my calculator is not able to keep up with me as fast as I press that button, but that's how that works. Okay, so when I go back to my graph, as I move off the right side of the graph, my end behavior would be 3 in this case. As I move off the left side of the graph, and moving off the left side of the graph would just be telling you that your x values are getting closer and closer to negative infinity. So I'm moving off the left side of the graph. And as I move off the left side of the graph of that same function, I want to know what's happening to your y values. Well, again, your y values are getting closer and closer and closer to 3. Okay, so this is the left edge, and this is the right edge. All right, and we'll do another one here. 3x cubed over x squared plus 1. 3x cubed over x squared plus 1. All right, go ahead and hit graph. Okay. By the way, on that last one, I had a horizontal asymptote. Hopefully you could see that. And it was a horizontal asymptote, if you can picture that last one, because it was approaching a number right here. If you have a horizontal asymptote, it will be approaching a number as you move off either the left side or the right side. Okay. On this one, I don't have an asymptote, and so you'll see how it's a little bit different. Okay. On this one, when we graph it, this is 3x cubed over x squared plus 1. When we graph it, as I move off the right side of the graph, and I keep moving right, my y values are getting higher. So on the right side, my limit as x approaches positive infinity, all that's telling me is I'm moving off the right side of the graph. And again, my function was 3x cubed over x squared plus 1. Okay, your answer is basically going to be what's your y value doing? Well, your y value is getting higher and higher and higher, so it is approaching positive infinity. Okay, so that's the right side. The left side in this case, as I move off the left side of the graph, I continue to go down and down and down and down and down. So my limit as my x's get smaller or approach negative infinity, again, that's just telling me you're moving off the left side of the function 3x cubed over x squared plus 1. My y values are getting smaller and smaller and smaller and smaller and smaller because I'm moving down. So my y values are at negative infinity. Okay, and that's how I would analyze end behavior. Notice that these are approaching negative and positive infinity on either side, not approaching a specific number, and therefore I do not have a horizontal asymptote. Okay, if you're getting close to a specific number, you have a horizontal asymptote. If not, you don't. Okay, so that's what end behavior would look like, and that's this lesson.